to the next topic, solubility. Solubility of a substance is its maximum amount that can be dissolved in a specified amount of solvent at a specified temperature. It depends upon the nature of solute and solvent as well as temperature and pressure. Let us consider the effect of these factors in solution of a solid or a gas in a liquid. So solubility, what is solubility? This might be asked as a definition question where define solubility. So solubility of a substance is the maximum amount that can be, is its maximum amount, that is the solubility of salt in water is nothing but the maximum amount of salt that can be dissolved in the specified amount of water, which is your solvent, at a specific temperature. Like you would have seen, so we add salt in water, we mix it and it gets mixed, again we are adding some more salt, again it is mixing well, but after some time it wouldn't mix properly and it will start settling at the bottom. This time when you heat it, again there are molecular spaces created in between the water molecules, and these salt molecules are going and settling in between them. So when you increase the temperature, again you see that salt dissolves in water. That is why they have specified here that solubility of a substance, right, solubility of a substance is its maximum amount that can be dissolved in a specified amount of solvent, which is very very important. Specific amount of solvent, when you increase the amount of solvent, again this solute would be able to mix well, right, would be able to dissolve. Again when you increase the temperature also, the solubility differs. So that is why solubility of a substance is its maximum amount that can be dissolved in a specified amount of solvent at a specified temperature. Now there are factors on which the solubility depends upon. As we saw now, already we saw that amount of solvent is important, also the temperature is important. When you increase the temperature, solubility increases, like for few cases, not always, that we'll be discussing later in the chapter. So it depends upon the nature of solute and solvent. Nature of solute and solvent, nature in the sense the solute should be able to dissolve in solvent. For example, again we'll be seeing this in the next few slides, that only like dissolves in like, that is an organic solute cannot dissolve in an inorganic solvent. Again an inorganic solute cannot dissolve in an organic solvent. So nature of solute and solvent are important, as well as the temperature and pressure are also important. If the temperature is low, then the dissolving rate or the solubility rate will be less, and the pressure also, if the pressure is high, then the solubility will be a little greater. Now let us consider all these facts and let us learn about how these factors affect the solution of a solid or a gas in a liquid. Solubility of a solid in a liquid. So first we'll be focusing about solubility of a solid in a liquid. Every solid does not dissolve in a given liquid. While sodium chloride and sugar dissolves readily in water, naphthalene and anthracene do not. On the other hand, naphthalene and anthracene dissolve readily in benzene, but sodium chloride and sugar do not. It is observed that polar solutes dissolve in polar solvents and non-polar solutes in non-polar solvents. In general, a solute dissolves in a solvent if the intermolecular interactions are similar in the two, or we may say like dissolves like. So just before I told you that organic doesn't dissolve in inorganic and inorganic doesn't dissolve in organic. There is the same thing that they have mentioned here. So they have talked about polar and non-polar solutes and solvents, right? So naphthalene and anthracene are non-polar, and so they cannot dissolve in a polar solvent like water. Similarly, non-polar solutes like sodium chloride and sugar do not dissolve in polar solutes like sodium and chloride do not dissolve in non-polar solvents like benzene. So this depends on the nature of solute and solvent, that is their intermolecular interactions should be similar for them to dissolve. For the solubility of the particular component, that component should have similar intermolecular interactions as that of the solvent. That is what they say, that like dissolves like. Now, when a solid solute is added to the solvent, some solute dissolves and its concentration increases in solution. This process is known as dissolution. Some solute particles in solution collide with the solid solute particles and get separated out of the solution. This process is known as crystallization. A stage is reached when the two processes occur at the same rate. Under such conditions, number of solute particles going into the solution will be equal to the solute particles separating out, and a state of dynamic equilibrium is reached. So this also is one of the very important definitions that might be asked again and again. This process is this process is known as dissolution. So they might ask dissolution, what is dissolution, or define dissolution, right? So dissolution would be when a solid solute is added to the solvent. Two things would happen. One is that some of the solid particles would sorry one of the yeah some of the solid solute particles dissolve into the solvent, and the concentration of the solute would increase in that particular solution. Now this dissolution, this process of the solute getting dissolved, is known as your dissolution. The other thing that might happen when the solid solute is added to the solvent is that the solid particles will collide with the solid solute particles. The particles which is present in the solution would collide with the particles that you are adding into the solvent. Now there might be this collision happening, and some of the solute particles get separated out of the solution. Now this process is known as crystallization. So again, let me tell you, when you add the solid solute into the solvent, two things would happen. One is dissolution, the other one is crystallization. Both of them happen at the same time. They happen simultaneously. One is that some of the solute particles get dissolved in the solution, dissolved in the solvent, and the concentration of the particular solid solute particle would increase in the solution. Now this process is dissolution, right? It gets dissolved and it is dissolution. Talking about crystallization, when you add the solid solute particle, the already present solute particles in the solution will collide with the solid solute particle that you are adding in, and now this collision would take place, and some of the solute particles would get separated out of the solution. Now this process is known as crystallization, and both of them, as I told you, occur simultaneously. Now when there is a stage is reached when the two processes occur at the same rate, that is number of particles dissolving and the number of particles getting crystallized, both will be at the same rate. Under such conditions, number of solid particles going into the solution will be equal to the solid particles separating out of the solution, and this state would be a dynamic equilibrium state. Now solute plus solvent gives solution, and this is a equilibrium expression. Now, at this stage, the concentration of solute in solution will remain constant under the given conditions, that is temperature and pressure. Similar process is followed when gases are dissolved in liquid solvents. Now, we were talking about solid solute particles. Now, they are saying that gases, even if the solute is gas, then similar process takes place. So, as we saw that it will reach a dynamic equilibrium stage, and after this, not after this, but at this stage, the particles getting dissolved and the particles getting crystallized will be equal. That means the amount or the concentration of solute staying in the solution will remain constant. There won't be any change, because something getting in and something getting out, both are equal. Then something staying inside the solution will be constant, right? Under the given conditions like temperature and pressure. Now, such a solution in which no more solute can be dissolved at the same temperature and pressure is called a saturated solution. When this equilibrium stage is reached, your amount of concentration will remain concentration of solute would remain constant, and if this concentration of solute has reached its maximum, that is no more solute particles can be added into the same solution at the given temperature and pressure, then that particular solution is called as saturated solution. We would have learned this in our earlier classes already. Then an unsaturated solution is one in which more solute can be dissolved at the same temperature, that is, there is still space in the solvent for dissolving the solute, and again there is the stage, that is number of particles getting in and number of particles getting out will be same. Then this stage at which more solute can be added, that is, there is still space, as I told you, there is still space in the solvent to dissolve the solute. Then this particular stage would be called as unsaturated solution at the same temperature. See, they are mentioning this point again and again, that same temperature and pressure, because these affect the solubility. So when you change the temperature and pressure, there might be an increase in the solubility or there might be a decrease in the solubility. A solution which is in dynamic equilibrium with this undissolved solute is a saturated solution and contains the maximum amount of solute dissolved in a given amount of solvent. Thus, the concentration of solute in such a solution is its solubility. So, let me read it again. The solution which is in dynamic equilibrium, that is a stage where solutes getting in and solid particle getting out, both will be equal at the rate would be same. Then dynamic equilibrium with undissolved solute is a saturated solution and contains the maximum amount of solute dissolved in a given amount of solvent. Thus, the concentration of solute in such a solution is its solubility. So, the maximum amount of solute that can be dissolved in the given amount of solvent would be reached when that is in the saturated solution. So in the saturated solution, maximum amount of solute would be already present, that is after this you can't add any more, that is only your saturated solution, right? So when you measure the amount of solute that is present in the solution, and that would be the maximum concentration of the solute that can be dissolved in the solution, and this will be called as a solubility of the solute. Thus the concentration of solute in such a solution is its solubility. So the amount that can be dissolved in this particular solvent at this particular given amount of solvent at this particular temperature and this particular pressure would be called as your solubility. Earlier we have observed that solubility of one substance into another depends on the nature of the substance. In addition to these variables, we also saw that it depends upon temperature and pressure. That is, temperature and pressure also controls this phenomena. Now talking about the effect of temperature in solubility of solid or gases, the solubility of a solid in a liquid is significantly affected by temperature changes. That is what we saw when we mix salt, when we dissolve salt into water, then you increase the temperature, then more solute can be added into the solvent. Now consider the equilibrium represented by equation 1.10. This being 1.10 is nothing but this one, solute plus solvent gives solution. Yeah, so getting back, effect of temperature. So this being dynamic equilibrium must follow Le Chatelier's principle. In general, if in a nearly saturated solution, the dissolution process is endothermic. Why they are stating it as nearly saturated solution? Because there won't be any extra solute present which is not being able to dissolve, right? So nearly saturated solution, at the point of saturation, the dissolution process is endothermic, that is H-sol will be greater than 0. Then the solubility should increase with rise in temperature, and if it is an exothermic reaction, then at H-sol, that is H-sol is less than 0, the solubility should decrease. These trends are also observed experimentally. So that this point I have given as a table here. Saturated solution, if it is endothermic, remember carefully, endothermic means it absorbs energy and the reaction takes place. Then if it is endothermic, then your solubility will increase with increase in temperature, because when you give energy, the temperature increases. Then when you provide energy, that is an endothermic reaction, right? So when you provide energy, temperature increases. Also your when you provide energy, the reaction takes place, so solubility also will increase, right? So that is what is the logic here. Endothermic means the solubility will increase with increase in temperature, whereas if it is exothermic, then energy is released, temperature will decrease. Temperature energy is released, then temperature increase will decrease the solubility, right? So for endothermic, for nearly saturated solution, endothermic reaction, then solubility will increase with increase in temperature, that is straightly proportional, directly proportional probably. Then exothermic, if the solubility will decrease if the temperature is increased. Now coming to the effect of pressure, pressure does not have any significant effect on solubility of solids and liquids, because solids and liquids are highly incompressible and practically remain unaffected by changes in pressure. Now pressure is not an important factor, or it does not play any significant role in the solubility of solids, because solids and liquids are highly incompressible, so they do not get affected by the changes in pressure. Now getting to the next topic, solubility of a gas in liquid. Many gases dissolve in water. Oxygen dissolves only to a small extent in water. It is this dissolved oxygen which sustains all aquatic life. On the other hand, hydrogen chloride gas HCl is highly soluble in water. Solubility of gases in liquids is greatly affected by pressure and temperature. The solubility of gases increase with increase of pressure. For solution of gases in a solvent, consider a system as shown in figure 1.1a. I have not provided the picture here, but you could see in your Ncert. There is a system provided there with a gas, with solution, and with a weight W1. The lower part is solution and the upper part is gaseous system at pressure P and temperature capital T. Assume the system to be in a state of dynamic equilibrium. That is, under these conditions, rate of gaseous particles entering and leaving the solution phase is the same. Now increase the pressure over the solution phase by compressing the gas to a smaller volume. Figure 1.1b. Again, the figure is given there. They have given three more weights, W1, W2 and W3, and they have compressed the gas in 1.1b. This will increase the number of gaseous particles per unit volume over the solution and also the rate at which the gaseous particles are striking the surface of solution to enter it. The solubility of the gas will increase until a new equilibrium is reached, resulting in an increase in the pressure of a gas above the solution, and thus its solubility increases. So from this we understand that the solubility of gases in liquids are greatly affected by pressure and temperature, and also solubility of gases are directly proportional to the change in pressure. That is, they increase, solubility of gases increase with increase in pressure. Now they have given two figures, and they have said that the amount, see, the gas in solution are present in 1.1a, figure 1.1a. They say that there it is in an equilibrium state where the amount of gas particles entering and leaving the solution are same. Now when they increase the pressure, the more particles, more number of gaseous particles strike the solution. That is, as the compression takes place, the particles also get closer to the surface of the solution. Agree? Now closer to the surface of the solution, right? Now the gaseous particles striking the surface of the solution also will be greater, because more number of particles are near the surface, then striking rate also will be more, so entering into the solution also will be greater. That is why the solubility of the gas will increase when the pressure is increased until a new equilibrium is reached, resulting in the increase in the pressure of a gas above the solution, and thus the solubility also will be increased. Now, Henry was the first to give a quantitative relation between pressure and solubility of a gas in a solvent, which is known as Henry's law. So we saw that solubility is directly proportional to the amount of pressure applied for a gas. That is what we saw through experiments. Now this there should be a quantitative relation, right? So that was first proposed by Henry, and it was called as Henry's law. Now this orange part is very, very important, because again it is a frequently asked question. It is a one marker that state Henry's law. Okay, so what is this Henry's law talking about? It is talking about the relation between pressure and solubility. So the law states that at a constant temperature, the solubility of a gas in a liquid is directly proportional to the partial pressure of the gas present above the surface of liquid or solution. Always try to remember the image that is given in the Ncert figure 1.1. As I told you, there was gas present above the surface of the liquid or the solution, right? And they have taken a constant temperature. Now at the constant temperature, we saw that solubility of the gas in the liquid was directly proportional to the partial pressure of the gas present above the surface of liquid or solution. So at a constant, the law starts like it is at a constant temperature. Then we already know that solubility of the gas in the liquid is directly proportional to the pressure of the gas. Now they are saying it as partial pressure. So it is directly proportional to the partial pressure of the gas present above the surface of liquid or solution. Remember, try to remember the figure. There was constant temperature. Now then the solubility was directly proportional to the partial pressure, and the gas was present above the liquid or solution. Then Dalton, a contemporary of Henry, also concluded independently that the solubility of a gas in a liquid solution is a function of partial pressure of the gas. Again, this could be another state the following question, right? So solubility of a gas in a liquid solution is a function, is nothing but it is directly proportional to the partial pressure of the gas. If we use a mole fraction of a gas in the solution as a measure of its solubility, then it can be said that the mole fraction of gas in the solution is proportional to the partial pressure of the gas over the solution. Now to represent the solubility of the gas, they are using this mole fraction concentration term to be the better one. So mole fraction of the gas in the solution will be proportional to the partial pressure of the gas over the solution. The most commonly used form of Henry's law states that the partial pressure of the gas in vapor phase is proportional to the mole fraction of the gas in the solution. Again, this yellow portion is also important because they might ask the most common form of Henry's law, right? State the most common form of Henry's law. So that states that again all the statements say the same thing. Your Henry's actual law, and then Dalton's law, and then now this another form of Henry's law, all of them state that partial pressure of the gas that is to be dissolved in the liquid or in the solution in the vapor phase, that is proportional, when the gas is in its vapor phase, is directly proportional to the solubility of the gas or the mole fraction. Now we are taking the measure of solubility in terms of mole fraction. So mole fraction is directly proportional to the partial pressure of the gas above the solution, is what is stated in all the three statements here, and is expressed as P, where P is given as your vapor phase or the partial pressure in the vapor phase. Sorry, P is represented as the partial pressure of the gas in the vapor phase, is equal to, we know that P is directly proportional to X, where X is your mole fraction. Now to remove the proportionality sign, we are including a proportionality constant, which is your KH. Now KH is the Henry's law constant. If we draw a graph between partial pressure of the gas versus mole fraction of the gas in solution, then we should get a plot of the type as shown in figure 1.2. It is a linear plot, because we know again and again we know that mole fraction is directly proportional to the partial pressure of a gas dissolving in a solution. Then the graph also will be linear because they are directly proportional. So drawing a graph between partial pressure versus mole fraction would be a linear plot. Now different gases have different KH values at the same temperature, that is suggested in the table 1.2. This suggests that KH is a function of the nature of the gas. So as we saw that KH is a proportionality constant here, it is a function of the nature of the gas, that is different gases would have different KH values. It is obvious from equation 1.11. Your equation 1.11 is nothing but P is equal to KH into mole fraction, right? That higher the value of KH at a given pressure, lower is the solubility of the gas in the liquid. From that equation we can derive that your Henry's law constant and the mole fraction are inversely proportional. So your solubility will decrease if your Henry's law constant, that is KH, is higher. That is, higher the value of KH, lower will be the value of solubility. Again, when the solubility is higher, that means your KH value will be lower. Now it can be seen from table 1.2 that KH values for both N2 and O2 increase with increase of temperature, indicating that the solubility of gases increases with decrease of temperature. Now I have not given the table 1.2 also here, it is there in your Ncert. We can see that N2 at the temperature 293 Kelvin has KH 76.48 and the gas is formaldehyde. Now again N2 at the same at a greater temperature like 303, your KH is 88.84. that is, there is an increase in the value of KH with an increase in the temperature also. That is what they have mentioned. Again for O2 at the temperature of 293 has got KH value to be 34.86, and same O2 with the temperature at the temperature 303 has got its KH value to be 46.82, suggesting that your KH, that is Henry's law constant, is directly proportional to the temperature. So temperature increases, your Henry's law constant will increase. That means solubility will decrease. So indirectly from here we are able to find out that temperature and the solubility are inversely proportional. That is, when temperature increases, your solubility will decrease, and vice versa, when your temperature decreases, solubility will increase. That is what we are able to conclude here, because temperature and Henry's law constant are directly proportional from the table given. That means when Henry's law constant and temperature are directly proportional and Henry's law constant and solubility are inversely proportional, then your temperature and solubility of gas in a liquid are also inversely proportional. As we saw that Solubility of gas in a liquid is affected by pressure and temperature. By pressure, it is directly affected, that is, it is directly proportional, and by temperature, it is inversely affected, that is, when the temperature decreases, your solubility will increase. It is due to this reason that aquatic species are more comfortable in cold waters rather than in warm water, because in warm water, the dissolution, the rate of solubility of oxygen in water would be lesser as compared to cold water. So that is why aquatic species are more comfortable in cold water. Now, this Henry's law finds several applications in industry and explains some biological phenomena. Notable among these are given below. In your textbook, they have given it as 4 points, or I guess 3 points here, right? But this also is very, very important. There might be give reason type questions. They might ask you like, why is your soda bottle, soft drink bottle, sealed with under high pressure? Or they might ask what happens to the scuba divers. I'll explain to you the points here. So they might ask these points in your give reason type questions, which are like most predominant types of questions asked in chemistry. Give reason types are very predominantly asked types of question there. So they might ask this application of Henry's law very importantly, so that I have given you how I noted these points and studied for the board exam right here. I did this before board exam in a rough sheet, and I used this to remember or recall the applications of Henry's law. So I have pasted the picture here for all of you also to find it easy to understand this application of Henry's law. Now, the first point is, let me read it from the Ncert and also tell you from my notes here. So, to increase the solubility of CO2 in soft drinks and soda water, the bottle is sealed under high pressure. I have given you here to increase solubility of CO2 in soda or soft drink bottle. It is sealed under high pressure. When the pressure, as we saw that when the pressure increases, your solubility of CO2 will also, solubility of gas will also increase, right? So that is why they are sealed under high pressure, for the greater solubility of CO2 in the soda water or soft drinks. Second point, scuba divers must cope with high concentrations of dissolved gases while breathing air at high pressure under water. Increased pressure increases the solubility of atmospheric gases in blood. So scuba divers must cope with high concentration of dissolved gases while breathing air at high pressure underwater. So underwater there will be high pressure. So the scuba divers will have to face high concentrations of dissolved gases. Again, we know that high pressure, then solubility will be more. So concentration of dissolved gases will be more. Now, increased pressure will increase solubility of atmospheric gases in blood. So now the pressure outside the scuba diver, say in water, is greater. That we saw high pressure is there under water. Now this high pressure will aid in increasing the solubility of atmospheric gases in blood, right? Outside there is high pressure, then automatically your high pressure will, that this it will help in solubility of atmospheric gases in the blood. At surface, the pressure will decrease gradually. As the pressure decreases, gases are released in the blood. Now underwater there was high pressure, so it aided in the increase of solubility of atmospheric gases in blood. Now when you go to the surface does not have that much high pressure, right? So the pressure decreases gradually. As the pressure decreases slowly, the gases are released in the blood which the gases which was dissolved in the blood now has to get released in the blood, because now the pressure in the blood is higher than the pressure outside. At the surface I'm talking about, at the surface your pressure in the blood would be higher than the pressure at the surface. So now there is again a transition of gases from higher pressure to lower pressure. So the gases are released in the blood, forming bubbles of N2 in blood. So generally the air has got maximum amount of N2, right? So when the gases are released in the blood, bubbles of N2 are formed in the blood. Now this bubble can block the capillaries, causing bends. Bends is a phenomena which is painful and dangerous to life, right? The nitrogen bubbles can block the capillaries and create a medical condition known as bends, which are painful and dangerous to life. To avoid bends, so now scuba divers have cannot avoid diving into the water. So instead of that, to avoid bends, to avoid this This also cannot be avoided generally, because there is high pressure underwater and there is only low pressure at the surface. So this is a naturally occurring phenomena. So to avoid this medical condition called bends, the tanks that they carry, as well as to avoid the bends and as well as the toxic effects of high concentrations of nitrogen in the blood, the tanks used by scuba divers are filled with air diluted with helium. It is diluted with helium. Now they have given the percentage also: 11.7 percentage of helium, 56.2 percentage of nitrogen, and 32.1 percentage of oxygen would be added into the cylinders of the divers. Now they can avoid bends because there is helium present. So there won't be this condition called bends, because the nitrogen amount of nitrogen is being reduced. So you won't there won't be the formation of N2 bubbles, and that won't block the capillaries as well. Now coming to the next application, at high altitudes the partial pressure of oxygen is less than that of the ground level. Now we saw underwater the pressure was greater than the surface level. Coming to high altitudes, at the surface, at the sea level, your pressure will be greater as compared to higher altitudes. The partial pressure of oxygen is less than that of the ground level. This leads to low concentration of oxygen in the blood and tissues of people living at high altitudes or climbers. Low blood oxygen causes climbers to become weak and unable to think clearly, symptoms of a condition known as anoxia. So again, at high altitudes partial pressure of oxygen would be lesser. When the oxygen content in your blood is less, there might be so many problems that is caused. That is why we are always insisted to drink more water, because water also contains oxygen, right? So constant supply of oxygen, and we breathe every single second. We can't be alive without breathing, right? We breathe in oxygen every single second because oxygen is very essential in the blood. So now people at higher altitudes or climbers going to higher altitudes, they might face this problem because oxygen concentrations are lesser there. So oxygen in your blood also will be at low concentrations. Now this can cause weakness. This can make people unable to think clearly, and this is a symptom of a problem or a condition called as anoxia. We can unable to think. So this is all about Henry's laws applications. Now, effect of temperature on the solubility of gases. We already saw that temperature is inversely proportional to the solubility of gases. So solubility of gases in liquids decreases with rise in temperature. I have highlighted decreases and rise. So solubility decreases with rise in temperature because they are inversely proportional. When dissolved, the gas molecules are present in liquid phase, and the process of dissolution can be considered similar to condensation, and heat is evolved in this process. We have learnt in the last section that dissolution process involves dynamic equilibrium and thus must follow Le-Chatelier's principle. As dissolution is an exothermic process, the solubility should decrease with increase of temperature. They have stated the reason why there is a decrease in the solubility when there is an increase in the temperature. So the gas molecules are present when they are dissolved. They are present in the liquid phase. When they are getting dissolved, they are present in the liquid phase. Now the process of dissolution can be considered similar to condensation, right? From their vapor phase they are getting into liquid phase when they get dissolved. You understand, right? We talked about the gas being in vapor phase. We were talking about partial pressure of the gas in vapor phase. So from the vapor phase it is getting converted to its liquid phase, similar to condensation. Then when condensation happens, there is a release of energy, of course, because this is a reverse of gas becoming into liquid. So there is a release of heat there. Now when there is a release of heat, that means it is an exothermic process. And in the earlier section we saw that following Le-Chatelier's principle, if it is endothermic, then your solubility will increase with increase in temperature, and if it's exothermic, your solubility will decrease with decrease in temperature. That is the reason why solubility of gases and liquids decreases with rise in temperature. With this, we have come to the end of this video. Thank you for watching. If you found this video helpful, please like and subscribe for more educational content. Don't forget to hit the notification bell so you never miss an update. Your support helps us create more valuable resources for learners like you. Keep exploring and stay curious. Bye.